In this video, we'll look at conditional probability, which lets us determine probability when we already know some information ahead of time. Let's take one last look at our gumballs. And remember, some of them are spicy. Suppose you reach into the jar and pull out a gumball, and you can see that it's red. Given that information, what can you now say about the probability that it's spicy? This is an example of conditional probability, where we know some condition ahead of time, and that gives us new information about the probability. We write out conditional probability like this, with a vertical bar, and we'd read this out loud as the probability that the gumball is spicy given that it's red. So you can read the vertical bar as given, and remember that the extra information, the condition that we know, is what comes after the vertical bar. So since we're given that the gumball is red, we can restrict ourselves to just looking at the red gumballs and ask how many of them are spicy. Out of 5 red gumballs, 2 of them are spicy. So the probability that the gumball is spicy given that it's red is 2 out of 5, which comes out to 0.4. We can also calculate conditional probabilities using other probabilities we already know. If we take the probability of being red and spicy and divide it by the probability of being red overall, we also end up getting the same probability, 2/5. In either case, our denominator contains our given information, our condition, and the numerator combines it with the other thing we're trying to find out. Now, whenever we're doing conditional probability, we have to be very careful about which information is given to us, because switching the order of the statements usually leads to different results. For example, suppose you pull out a gumball and you don't look at its color, you just pop it in your mouth, and notice right away that it's spicy. We could ask, what's the probability that you happen to get a red gumball? This time, being spicy is the given information that we already know, and being red is the new information we're trying to find out. So now, since we already know the gumball is spicy, we're restricting ourselves to just the 3 spicy gumballs. Of those, 2 are red. So the probability of the gumball being red, given that it's spicy, is 2/3. Again, we can use the individual probabilities to calculate this. And once again, the given information is what goes in the denominator. Here's how we could write our result as a general formula. If we have some given information A, a condition, then we can put the probability of A in the denominator, since we're restricting ourselves to only consider cases that include A. And then the numerator contains all the events that also include B as well. By the way, using a little bit of algebra, we can rearrange this equation to get a more general formula for the probability of A and B, by imagining the 2 events happening one right after the other. First, A happens, and then given that A happened, B happens as well. And then we can multiply those together. This explains the drawing multiple gumballs without replacement problem that we saw in the last video. Given that we've already drawn a red gumball, the probability of drawing a blue gumball has changed to 3/9. If the first gumball we'd drawn was blue instead of red, we'd end up in a very different situation, since now we'd not only have 1 fewer gumball overall, but also 1 fewer blue gumball as well. Let's look at how conditional probability relates to independence. We already know that the probability of being spicy, given that the gumball is red, is 2 out of 5. What if the gumball isn't red, though? Well, if we concentrate on the blue and yellow gumballs instead, now only 1 out of 5 is spicy. So the probability of a gumball being spicy, given that it's not red, is 1/5. This is actually one way to show that being red and being spicy are not independent events. If they were, the chances of being spicy would be the same, regardless of whether the gumball was red or not. We can also show this by trying the multiplication rule. There's a 5/10 chance of being red and a 3/10 chance of being spicy. But if you multiply those together, you don't get the correct probability of being red and spicy. So this is another way to show that these two things are not independent. So all in all, here's a summary of how we calculate probabilities. These tell us everything we need to know about how to combine different events, using the complement rule to find the probability that something doesn't happen, and then using the multiplication rule and the addition rule to deal with ands and ors, respectively. And finally, we have a few simplifications that we can make when we know that two events are disjoint or when we know they're independent. By the way, a quick note about memorization. It's possible to break all of these down into formulas for specific cases, like how to deal with OR statements for disjoint events, or how to deal with OR statements for independent events. But I think you'll have a much easier time remembering these if you understand why they work intuitively. And I've done my best to try to explain that myself in these videos. So if you haven't already, take some time to think about the things listed here and what the key intuition is for why each one is true, so that rather than just following formulas, you can be confident in your understanding.